All right, today, day 2 of section 5.4, which focuses on sum difference formulas. So, quick recap. What we have is a set of 6 formulas that we can condense down to 3. The way we read that plus minus, and that plus minus is whatever this is, that's the same. We're not taking 2 different roots. We're not doing the problem twice, which is sometimes what that plus minus indicates, but not in this context. This is going to be the opposite of that. These guys are the same. Those guys are opposites. We are going to continue with what are some contexts that we can use this in. First for today is going to be, well, how would this look as part of a SOHCAHTOA right triangle problem? Well, since we're talking about 2 different angles, usually they're going to be 2 different triangles, or in this case, a composition of 2 triangles. So up here, we have a 5, 12, 13 right triangle, and that angle X is going to be our angle of interest. Okay, down here, we have 11, root 23, 12, not one of the more common right triangles, but if you check it, it is a Pythagorean triple, it's valid. And our angle of interest there is Y. So given this picture, what's the sign of y minus x? All right, well, the same as almost anything else you ever do in math, the order of subtraction is important. Which one comes first, which one second matters. So that's in the U slot, that's in the V slot, referring back to our original formula. The pattern for sine, sine, cosine, cosine, sine, sine, cosine, cosine, sine. First, second, first, second. First, second. Now, when we did a problem similar to this yesterday, what had happened was once we hit this stage, those values could come directly from the unit circle. Well, in this case, we're not in the context of the unit circle, we're in the context of right triangle trig. So we have to get these values from that picture. So the sine of y is going to be root 23 over 12. The cosine of x, 12 thirteenths. Cosine of y, 11 twelfths. Sine of x, 5 thirteenths. Okay, once we have all these values in here, similar to what we did yesterday, it just becomes order of operations. Multiply these 2 fractions together, multiply these 2 fractions together. Usually you make a single fraction out of it, and that tends to be kind of the flavor, so to speak, of what these answers look like. Okay, next context we're going to look at. How would this play out when you are dealing with questions that are being described as angles in standard position or rotations in the coordinate plane? So, probably need to zoom out a little bit in this because we've got to add a little bit to this picture. Okay, given that the sine of u is negative 3/5 and the secant of v is 13/12, what's the secant of u plus v? All right, well, when we're talking about rotations in the coordinate plane here, we have to make sure that we draw them in the correct quadrant. So this statement by itself is not enough to locate the angle. They have to give us more information. U being between pi and 3 pi over 2, that's the 3rd quadrant. So when we sketch U, we need to draw it as a 3rd quadrant angle. So there's our U in there. Sine, negative 3/5. This must be a negative 4. And we have a picture to represent angle U. Okay, secant of V being 13/12, I would prefer to make that cosine of V is equal to 12 thirteenths. Between 0 and pi over 2, that's the 1st quadrant angle. So there's our V. Cosine 12 thirteenths makes that a 5. All right, now we don't have a formula for the secant of a sum, so what we have to do is rewrite this as 1 over cosine. Then the bottom of that gets expanded out with the appropriate formula from here. Cosine is cosine, cosine, sine, sine. First, second, first, second. First, second, first, second. Now once we get this guy right here, now we have to fill in those values. Yesterday, we did problems where those values came from the unit circle. The slide that we just finished, the values came from a right triangle. Now the values are going to come from these two angles in standard position. So the cosine of u is going to be negative 4/5. That goes here. Plug in all the rest of those three. Now it becomes order of operations. Multiply those fractions, multiply those fractions. Add those together. 1 over a fraction just flips the fraction, and that answers the final question. All right, next context. How would this play out in an equation solving situation? So, for example, we spent the entire section 5.3 talking about advanced algebraic and trigonometric techniques to solve equations. What would happen if we applied that here? So this is our equation. So when we see something that looks like this, when you have the sine of a sum, cosine of a difference, or usually the clue is they don't have to be a sine and a cosine. It would be two expressions within the same equation that both had that sum difference flavor to them. That's usually your clue that you want to use these formulas. So what you would do is take that first one, expand it out using the appropriate formula. Take the second one, expand that out using the appropriate formula, and then emphasizing here, don't lose that. So if it's minus this expression, and this expression expands out to multiple terms, ultimately that minus sign has to distribute it. Right. What you can typically expect when you are applying sum difference formulas to solving equations is this is going to expand out to be rather big and nasty. It should significantly simplify down within a step or two. So for starters, what we're going to do is evaluate everything that can be evaluated. So that, evaluate from the unit circle. 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 Okay, then the next thing that was done on this slide is they decided to distribute through with this negative sign. So the negative times that gets us here. The negative times the plus gets us there. All right, now you can start looking for some stuff that's going to cancel out. This and this, they're opposites of each other. Go on. That gets us to this line right here. Negative half sine x minus half sine x, that's negative 1 sine of x. A half and a half is just 1, so negative a half is negative 1. The negatives cancel, and then we can finish this problem up regular, normal, every day, off the unit circle. The sine of what angle is a half, and we're looking for the 0 to 2 pi interval. One of the things we discussed in section 5.3 was some equations have high risk of extraneous solutions. Equations that have high risk of extraneous solutions, you have to check the solutions. These tend to have a very low risk of extraneous solutions. I will not give you anything on a quiz or test where you have to check them for this type. The ones that do have the high risk, and you've already identified which ones they are, you have to make sure that they get checked. All right, comparing and contrasting. Okay, this equation right here, we saw that in section 5.3. If you have the type where it's a single trig function of a sum or a difference, what we did was we treated this as one big variable. The sine of what angle is root 2 over 2. So that thing is root 2 over 2 at pi over 4, 3 pi over 4. For this type, we always initially considered all solutions, regardless of whether it was all solutions or that interval. So this right here successfully solves the angle for x plus pi over 6. Then what we have to do is get those pi over 6's over to the right. So pi over 4 minus pi over 6. 3 pi over 4 minus pi over 6. When you combine those fractions, it gets you to there. Combine those fractions, gets you to there. So now with this line, we found all solutions to that equation. We don't want all of them, we only want 0 to 2 pi. So you have to start either physically or mentally making a list in terms of what angles are being represented by these, and then choosing the ones that fit the interval. Turns out there are only 2 that fit that interval, pi over 12, 7 pi over 12. Okay, as a what if we decided to solve this problem using the appropriate sum difference formula? Does it make it easier? Does it make it harder? Maybe it doesn't matter. So let's take a peek to see how this would play out. So sine of the first, cosine of the second, cosine of the first, sine of the second equal to root 2 over 2. That can be evaluated. That can be evaluated. Okay, that gets us to a point where we have a sine to the first, cosine to the first in the same problem. Okay, this goes back to day 2 of section 5.3. When this happens, the next thing we'd have to do is square both sides. Okay, when you square both sides, you typically want a single trig function on the left, single trig function on the right. So one of these guys needs to come over there. So the author of this decided to bring the cosine over there. That gets us to there. Square both sides. Okay, that's pretty clean. This has to be FOILed out. All right, now we have cosine squares and cosines mixed in the same equation. When this happened, what we did was we got an FFF, factor-friendly form, and once we get here, we realize, well, that doesn't even factor. So now what do you have to do? This is a strategy that is covered in section 5.3 that we didn't go over because it's an extremely long, tedious one. What you'd actually have to do is finish this up using a substitution with the quadratic formula. So this has the same algebraic structure as 4a squared minus 2 root 2a minus 1. So if we let cosine of x be a, we can get that, use the quadratic formula, substitute back in, and this is what our answer ends up looking like. And if you check those two guys, they're the same decimal approximations as pi over 12, 7 pi over 12. All right, you're never going to be responsible for a quiz or test that I give you in this class to be able to do that method. And it would be, it's a good 5 to 10 minute problem to make your way through that. It's just an impractical question. The idea here is knowing what strategy to do when. When you take a quiz or test, how do you know which strategy should apply to each problem? Well, if you do all the classwork and you do all the homework and you practice these guys before quizzes and tests, you should have a feel for what works when. It's just a matter of experience. You've done enough of these where you realize, hey, this is a good strategy, or no, it's not. And for this one here, other than just, it doesn't feel like you should be doing this, if you only have a single trig function of a sum or difference, that 5-3 strategy almost always is going to be the better option. If it's just a single trig function with a sum or difference, this tends not to work out very well. This illustrates that not working out very well. In contrast to when there are two of them in the same problem, that's when you typically want to do that. All right, last context in terms of how does this fit into, or how do these formulas fit in to the bigger picture of what we're trying to accomplish here. All right, mixing this together with our inverse trig functions. So we want to simplify sine of the arc cosine of 1 over x plus the arc cosine of root 3 over 2. So we're blending together what we did in section 4.7 with what we're doing now. Well, one thing to look for with these guys is there something that can be evaluated right away. Arc cosine of root 3 over 2. We know how to answer that. Spent the better part of 4 or 5 days talking about inverse trig functions. That's pi over 6. So that gets us from here to here. Now what we need to do is expand this out using the sine sum formula. So sine of the first, cosine of the second. Cosine of the first, sine of the second. Okay, now at this stage, what can we evaluate right away? Well, sine of pi over 6 is a half. Cosine of pi over 6 is root 3 over 2. This here, if these guys are inverses of each other, and we don't have any violation of restrictions like we talked about in 4-7, they're going to simply undo each other. And when this is algebraic, we kind of always made that assumption of its first quadrant, don't worry about intervals, this, that, and the other thing. You can safely assume that they'll cancel each other out, and that's 1 over x. Okay, this right here becomes a tough part of the problem. The sine of the arc cosine of 1 over x. So, as a recall of what we did here, that's algebraic, assuming first quadrant. Okay, cosine of that angle, 1 over x. Get an expression for this. 1 squared plus b squared is equal to x squared. b squared, x squared minus 1. b, square root of x squared minus 1. Only need to take the positive root because we're assuming first quadrant. What's the sine of that angle? Opposite over hypotenuse gets us to here. All right, now it becomes a, let's simplify what's left, order of operations. Multiply together gives you this. Multiply together gives you that. And as you know from 2 days of doing this, usually we express that as a single fraction. And that right there will be our final answer. All right. That wraps up day 2 of sum difference formula.